colloquium by Naveen. And without further ado, over to you, Naveen.
Okay.
You can start.
Thanks, Varun. So sorry about that initial delay. It was cloudy here and I could not connect, so I had to relocate myself to different position. Okay. So my thesis is an exploration of a turbulent dynamos in rotating and shear flows. These rotation and shears are the common features that are observed in all astrophysical systems, ranging from the Earth, Sun, galaxies. Okay. So in this generic setup, when you have both rotation and shear, so my thesis explored about the fixed helicity case and the fluctuating helicity case of the turbulent flows, which can give rise to the large scale dynamo, which can lead to the large scale magnetic fields. So this is the basic outline of the talk. So I'll just give the brief introduction to the dynamos, and then I'll introduce the problem, which is the non-helical dynamo that is considered in this thesis. And then the helicity fluctuation in conjunction with shear has a possible resolution to explain the dynamo that is there in the seen in this non-helical turbulence. And this we do in the renovating flow setup. And then if time permits, I'll go on to the spatial part of the fluctuation of the helicity. And this we consider in the mean field setting. And where we show, interestingly, kinematic dynamo is possible in this regime if there are gradients in the fluctuations. So lastly, I'll conclude. So as we know, all the astrophysical objects like Earth, Sun, galaxy have the magnetic fields of different order, and the scale of the magnetic field also varies in these galaxies to the size of the system itself. So for example, in case of the Sun, it has a dipolar magnetic field, and its scale of variation is the size of the Sun itself. Even in galaxy, as you can see in this diagram, it's a magnetovector diagram. These black dotted lines are the alignment of the magnetic field, which are aligned in the direction of the spiral arm of the galaxy. This also has a large scale feature. Let's say if the galaxy is of the order of 60 kiloparsecs, then the magnetic field can exist in such object on the order of 1 kiloparsec, and the strength of the magnetic field in these galaxies are found to be 10 power minus 6 Gauss. So generally all these objects have turbulent plasma in them, which has positive and negative charges. Because the protons are sluggish compared to the electrons in the movement, because of the fast movement of electrons, it can give rise to something called a tiny magnetic field, which are called battery effects, which are of the order of 10 power minus 20 Gauss. But the magnetic fields in these objects have survived for the time scale much longer than the turbulent diffusion time scale. Okay. So it's naturally begs for the question, what is the mechanism that has led to the generation of the magnetic field from this tiny seed field? So before going into this question, so let's look at a few equations that are needed for this dynamo. The basic equation is the induction equation, which is coming from the Maxwell's equation, Maxwell's Ampere's law, and then the Faraday's law, suitably combining with the Ohm's law in the non-relativistic limit. Then we get this induction equation. Induction equation has two terms. One is the advection term, another one is the diffusion term. Advection term basically carries the magnetic field. The magnetic field gets carried by the turbulent velocity field. So some of the features of this equation is, if you take eta to be 0, then there is something called flux freezing, meaning the magnetic field gets frozen onto the fluid turbulence, meaning in a given area, let's say there is some flux, and as the fluid evolves and if the area element changes, depending upon it decreases or increases, the magnetic field in it also varies, conserving the flux. So basically this is the term that is responsible for the dynamo action. So if you take the velocity field to be 0, then this is pure diffusion equation. And we can see in this equation, if B is equal to 0, it's a valid solution for the induction equation. So therefore, there is a need for the seed field to begin with. However small it is, there is a need for some seed field in this. Dynamo is basically nothing but a conversion of the kinetic energy from the fluid into the magnetic energy. Okay, it's basically an ordering mechanism. From the chaos, you are generating the order at the larger scale. So the next question is, what kind of flows can give rise to the dynamos? historically, people have looked at various different flows in laminar flows, in turbulent flows. So there is this one famous theorem which is important to know, and it also has an implication for the work that I present in this talk. So let's say if you have a 2D velocity field with the first component is not there, okay. The basic conclusion is for this 2D velocity field, you cannot have the dynamo. So the way to show is, like when you substitute this velocity field into the induction equation, considering the flow to be incompressible, the B1 component of the magnetic field obeys something called the advection diffusion equation. You can integrate this equation over the certain volume, and you can see that the energy that is there in the B1 component actually decays. On the right hand side, this is a positive definite quantity and eta is positive, so it always decays. So the B1 has B1 decays, the other two components of the magnetic field will also decay. To show the other components decay, we have to use the vector potential arguments. It is slightly more involved. Anyway, so in the 2D turbulence, okay, the dynamo cannot be sustained because of this anti-dynamo theorem, which was given in 1956 by Zeldovich. Why this is the case? Let's look at the simple toy model of the dynamo. Okay, let's say on the left hand side you have a flux ring, okay, with a magnetic field in it. Then because of the stretching effect of the fluid, let's say the magnetic field, the flux ring gets stretched to twice its diameter. Because the volume of the flux ring is conserved, its diameter gets, the area of the flux tube gets reduced, and because of the flux conserving theorem, the magnetic field in it gets enhanced. And then let's say there is a 8 kind of a folding that happens, a twisting operation, and then again there is a folding operation happens on this loop. Then this kink in the tube can be merged, can be diffused away with a little bit of diffusion, and then we get back the original configuration of the loop with twice the strength of the magnetic field. So you can see the operation third and the fourth, which is the twisting, and the folding operation is the out of plane motion operation. So the fluid has to push the flux tube out of the plane and then fold it back. So this operation cannot happen in 2D very naturally. That's the reason why we could not see the dynamo in the 2D system. So 3D structures are essential for the dynamo here. So in the turbulence, which has vorticities and vortex stretching and flipping of vortices, these operations can occur naturally. So once the Zeldovich introduced this model in 1972, people started developing turbulent dynamo theories. Till then, people were only looking at the laminar flows, which doesn't have a significant vortices in them. So now let's look at there are two kinds of dynamos. One is a large scale dynamo and the small scale dynamo. So the induction equation is written in this form by using the incompressibility limit and the divergence B is equal to 0. Basically, the magnetic field doesn't have a source or sink. So we saw previously that in this equation, this is an advection diffusion equation, it cannot give rise to the growth of the magnetic field. So compared to that, there is an additional term, which is the gradients of the velocity field. Okay. So if at all the growth has to happen, then the gradients of the velocity fields are very essential for the dynamo. So basically, the straining motion and the stretching motion for the fluids are necessary for the dynamo. Historically, it has been recognized two kinds of such gradients. One is the helicity, another one is the vorticity. The helicity is nothing but the component of the vorticity in the direction of the velocity field. Okay, it basically is like a screw-like motion of the fluid. When there is a screw-like motion of the fluid, then it can give rise to the helicity. Vorticities can naturally occur in the turbulent flows because they are the fundamental structure of the turbulence. And so once you have the helicity, the Parker showed in 1955 that it can lead to the large-scale dynamo action. So large-scale dynamo action means if you have a energy injecting scale of the turbulence at LF, okay, and the dynamo can occur on the scales which are much larger than the turbulent energy injecting scale of the turbulence. On the other hand, in the small-scale dynamo, because of the vortices and the randomness in the flow, the growth can occur on the scales which are smaller than the turbulence inducting scale. So in this talk on this thesis, our focus is mainly on the large-scale dynamo because we want to understand the magnetic fields that are seen in the astrophysical systems of large-scale magnetic fields. So the problem that is considered in the thesis is the following, that in the standard canonical dynamo theory, it is known that the kinetic helicity of the flow can lead to the large scale dynamo action. In case of, for example, in case of the solar convection zone, this helicity gets generated naturally. This alpha is nothing but the average kinetic helicity, which I will introduce later. So in the system like Sun, there is a rotation and convection, and as there is a rotation and when there is a temperature difference, a fluid blob starts rising, and a Coriolis force can act on this fluid blob, which can generate a gyrating motion, a helical motion. So that's how the helicity gets generated in this kind of a system. However, it was so in case of Sun, the turbulence is driven by the convection currents. However, in the galaxies, it is known that the turbulence is driven by the supernova explosions. Okay, so which can go off randomly in the galaxy, and the rate of occurrence of the supernova explosions are on the order of 1 in 20 years. And it's been estimated that the alpha, which is the average kinetic measure of the average kinetic helicity, is subcritical to trigger the dynamo in these galaxies. So people wanted to understand, without the helicity, can it give rise to the large scale dynamo action? So can non-helical turbulence give rise to large scale dynamo action? So simulators first jumped into this problem. Okay, what they did was, on the left you can see the galaxy, differentially rotating spiral galaxy. They took the local patch of this galaxy, and if you go to the local patch into the frame of rotation of this, then you can see that the differential rotation shows up as a shearing motion, and we take the shear to be along the direction of x2, which is the y-axis, and which is varying along the x1, which is the x direction. It is planar shear. Okay. So on top of this mean motion, they add the turbulence velocity field, which is okay. So this problem they are considered in the limit of incompressible limit, because to keep the thing simple, and the fluctuation velocity fields, the average, are considered to be 0. So in the simulation, you need they simulated two couple order differential equation, partial differential equation. One is the induction equation that I already introduced. It's just that it has now a mean motion shear added to it. Okay. And there is a Navier-Stokes equation, which is nothing but the Newton's second law for the fluid element. On the left hand side you have the acceleration, on the right hand side you have various body forces and surface forces, and there is a Lorentz force which is sitting here. In the simulation, they include something called the forcing function to introduce the randomness in the flow, because simulations cannot really hit the kind of RE that is needed to trigger the turbulence, especially in the incompressible limit. The RE one has to hit is more than 2000 or something. So that's why, to mitigate that problem, they introduce the forcing, which is randomly forced. For the simplicity, they'll do homogeneous isotropic and delta correlated in time forcing. Even though the forcing is delta correlated in time, the velocity field will pick up the correlation time because of the inertial effects of the fluid that is coming from the viscous force. So let's look at the few dimensionless quantities before showing you the plots of the simulation. So there is something called the magnetic fluid Reynolds number, which basically comes by taking the ratio of the nonlinear term to the viscous term. If R is greater than 1, that means the nonlinearity is very important. And then there is a magnetic Reynolds number, which you can define by the ratio of this advection term to this diffusion term. In astrophysical case, so for example, one can also define something called the Prandtl number, has the ratio of the magnetic Reynolds number to the fluid Reynolds number. In the astrophysical situation, both fluid Reynolds number and magnetic Reynolds numbers are much larger than 1. For example, in case of galaxies, it is of the order of 10 power 19, very ridiculously high. In Sun, it is 10 power 8. The Prandtl number, for example, which basically tells the separation between the dissipation scale in the fluid and the magnetic field. For the Sun and the Earth, it is less than 1, but for the galaxies, it is much larger than 1. So this is a simulation from Brandenburg. they have plotted the BRMS field, which is the total field, RMS value of the total field. Okay, so this is a log lin plot with the logarithm on the y-axis and the time scale on the linear axis. So you can see that the magnetic field grows in this non-helical turbulence. In this, here it grows linearly, means the growth is happening exponentially, and then there is a saturation occurs. So to know the large scale features of the magnetic fields in simulation, what they do is they take the average of the field. So they generally take the planar average, the xy average, and they plot the magnetic field in the z direction. So the mean fields, when you average over the turbulence scales, let's say the uninteresting scales of the magnetic fields, which vary over the turbulence scales, gets vanished. Only if the scales that are much larger than the turbulence scale will only survive, and it shows up in the plot. Here you can see that there is a large scale feature in the time and also in the space. So here both Rm and Re are larger than 1. Okay. So we wanted to understand this problem. So our motivation was theoretical. So therefore we wanted to do the simulation in the low Re case. The reason for doing simulation in the low Re case is that the nonlinear term becomes unimportant and it could be analytically tractable. So in this case, for example, the Re 0.6 and the Rm 32 and the forcing scale something like 5 times smaller than the box size, you can see that there is a large scale magnetic field growing in our simulation also. So if you look at the power spectrum plot of this simulation, this is the power spectrum plot in the saturated region, somewhere here, okay, 726 turnover time. So if you look at the kinetic spectrum, you can see that there is a sharp kink at the forcing scale, okay, and it just tapers off quickly. And the magnetic field has a power at the larger scale compared to the power at the smaller scale. So this sort of says that the nonlinear terms are not important. Predominantly the flow is only single scale in this simulation. Okay, if you contrast this with the case of the higher simulation, for example, if you look at the lower panel, you have both the magnetic field, which is shown in red, and the dotted line, which is the kinetic spectrum. You can see that it follows the Kolmogorov spectrum, okay, 5/3 rule. And there is in the lower one is a helical case. There is no shear in this. You can see the large scale feature, and we also see a large scale feature in this shear dynamo simulation without the helicity, net helicity. So this exercise basically indicated to us that the nonlinearity is not important. One can only, one can even understand this flow by considering the single scale flow. So in the simulation, what they have observed is, even though the helicity is 0, the mean of the helicity is 0, it has a wild fluctuation. Okay, this can be expected. This is natural to any turbulent systems. The fluctuations are always present. So, okay, before presenting, let me just briefly mention about the mean field equation that generally people use in this dynamo. So one can get this mean field equation by the induction equation by splitting the magnetic field into mean and the fluctuation part, and one can derive the equation for the mean magnetic field. And once they do that, the fluctuations, okay, at the turbulence scales will appear as alpha and eta t, which are turbulent transport coefficients, where alpha t is nothing but a finite, it is a measure of the fixed helicity. And then eta t is nothing but turbulence diffusivity, which is similar to the molecular diffusivity, but this diffusion is much stronger and happens at much larger scale compared to the diffusion scale. And this equation we have obtained by averaging the turbulent flow on particular scale, let's say L naught, and the time tau naught. Okay, and we are looking at the magnetic field at the large scale. So Kreitmann conjectured that, let's say if you have a helicity fluctuation in this flow, whose scales, let's say L alpha, is much larger than the fluctuation scale of the velocity field, then one can apply kind of an renormalization group technique to this equation, this mean field equation, and one can derive the mean field equation for this itself. Meaning, you take this equation, split the mean. The mean itself has a mean and fluctuation. Now the mean with b bar we call as a mesoscale field. Okay. So again, all the approximations that are used in the mean field theory are used here also. So Krigman found out that this mean field, which is average over the scale L alpha, obeys a diffusion equation. Okay, and he did this calculation in a delta correlated helicity fluctuation, alpha fluctuation, helicity fluctuations. When turbulence is homogeneous and isotropic, we can synonymously interchange these two words, alpha and helicity fluctuation. So Krigman showed that if the helicity fluctuations will augment the diffusion term, okay, and if helicity fluctuations are of certain strength, and if its strength crosses the diffusion in the turbulent field, it can lead to the growth of the magnetic field. And this alpha is considered, the average of the alpha is considered to be 0. Okay, on the scale of L alpha, it has a constant value on L naught, but it varies over the scale L alpha. So then people, this was proposed very long back, and people went and measured the turbulent diffusion in the simulations, and they found out, especially Brandenburg in 2008, that the turbulent diffusions are not negative. So then what we thought was, we decided to extend this model to the finite correlation effect, to include the finite correlation effect of the velocity field. Basically, this calculation was done for the delta correlated helicity fluctuations. So what we did was, as we saw that the only single scale flows are essential for this kind of a dynamo, we look for the single scale helical wave solution for the Navier-Stokes equation. So there we drop the nonlinear term. We also drop the viscous term, because once we drop the nonlinear term, the job of the viscous term is to only control the correlation time of the velocity field, which we anyway introduce artificially in a model later. So we look for this inviscid case, the shearing helical waves. These are having a sine or cosine. Basically, these are helically rotating vectors, okay, propagating in space. And the shear is actually acting on the wave vector of this wave and the amplitudes, okay. The wave vectors are getting sheared in this fashion, and the amplitudes, I'll show you the plots how they vary. So because of incompressibility condition, one can show that the wave vectors shear in a direction that is opposite to the shearing of the amplitudes. If you look at the plots of the amplitudes of these shearing waves, the one of the component, the A1 component, okay, looks like this, where the shear is sitting in the denominator, okay. So the time always sits with the shear in the shearing amplitudes. Anybody wants to ask a question? Okay, I heard some noise. Right. The amplitudes. Okay. The amplitudes, especially the U1 amplitude. Okay, if you plot it with respect to the shear, you can see that it gets sheared out. Okay, and if this is plotted for the particular initial condition where the U1 is 1 and then the other two components are 0. As the shear is increased, the energy that is present in one of the components get dumped into the other two components. Okay, for the only for moderate values of shear, the flow remains three-dimensional, but for the larger value of shear, the flow is quasi two-dimensional in a way. So this has an important implication for the dynamos that we see in this, because I already explained that for the 2D turbulence, okay, there is an anti-dynamo theorem which says that the dynamos cannot be positive limit. So now we use the renovating flow model to introduce the finite correlation effect into the model. So what they do here in renovating flow, basically it is motivated from the Markov renewing process from the stochastic processes. So here the velocity fields in the different intervals. So the time axis is basically split into the intervals of length tau, and the velocity fields in each intervals are distributed independently and randomly, and the velocity fields in one interval are independent compared to the velocity fields in the other interval. They are picked up independently from an underlying probability distribution. So that means the velocity fields are only correlated for this length tau, and it is uncorrelated after that time. Okay, it's basically kind of an artificial model, but because of this special points, the time stationary property of the fluid is compromised. But if you look at this model carefully, it is discretely time translational, okay, over the time tau, but our interests are only for the time which are much larger than this tau. So we want to look at the magnetic field at much larger time. So for the large times, we can consider this model to be time stationary in a way. So the velocity ensembles are specified. Here the velocity fields have a realizations in different intervals. Okay, so a particular ensemble is chosen. So the phase of the wave is varied from 0 to 2 pi, which gives a homogeneity condition, and the q is varied over the circle of radius q, and the amplitudes, the shearing amplitudes, the initial shearing amplitudes, basically they are varied over the circle perpendicular to q. So the A, C and Q are the orthogonal triad. So all the averagings in this calculations are done numerically. Okay. Okay. Let me just say how we obtained the magnetic field here in this model. So we looked at the model velocity field, which is the mean shearing motion plus the turbulence velocity, which is given by the single helical flow. And we look at the induction equation without the diffusion term, because in the astrophysical case, the diffusion is the eta is very small. So so it is also shown in certain theoretical calculation that eta doesn't make a contribution to the growth rate of the mean fields. Okay, it only makes a contribution to the second moment of the mean field, second order correlator. So once we drop the eta term, we have a ideal MHD equation, which is a flux freezing, it obeys the flux freezing theorem, and one can write down the Cauchy solution for this equation. So the initial magnetic field is advected by the velocity field basically, and this Jacobi matrix is nothing but a straining of the fluid animals. Okay, so the difficulty of solving the induction equation is now transferred to obtaining the Lagrangian coordinate basically of the fluid. So for this kind of a flow that we have considered, one can obtain the Lagrangian coordinate analytically, but if we consider complicated, then one has to do numerics for it. So only till here we go analytically, and rest of the averaging of the meaning the averaging over velocity ensemble, we have done it numerically. So we are interested in the Fourier mode of the magnetic field. Okay, we want to know what modes can grow and what modes can decay. So we define the Fourier transform of the average magnetic field. Okay, in this way. So it so the magnetic field in the Fourier space at n tau gets mapped to the magnetic field at n minus 1 tau through a response tensor. Okay, which is basically is some Fourier transform of this Jacobi matrix. So now if the eigenvalues of this response tensor is greater than 1, then it can lead to the growth of the magnetic field. Okay, if it is less than 1, then it can lead to the decay. So in general, this eigenvalue sigma is complex. To get the exponential growth rate, e power lambda t, where lambda is exponential exponent, it is related to the sigma, the eigenvalue, like this 1 over tau log sigma. So it has both the real part and the imaginary part. The real part of the dispersion relation will give you the growth rate, and the imaginary part will tell you the frequency of the wave. Basically, in case of sun, let's say you have sunspots which are migratory. So to get that migratory kind of a solution, you need to look at the omega. So one can compute the cycle period, of these waves. Basically, 11 year, 22 year of the suns are computed from this kind of a cycle period. So this response tensor has a two tensors to it. One tensor is called shearing matrix tensor, which is nothing but effect of shear, which adverbs the bx component in the by direction, in the y direction. So this is not that interesting. So the interesting quantity is the second one, which is the shear turbulence tensor. It has basically two terms. Okay. So this is the Bessel function of order 0, and this is the Bessel function of order 1, and there is a helicity of the flow which is sitting here, and both this Bessel function of order 0 and Bessel function of order 1 are even function in H. Okay. Let's say if you look at the strictly non-helical case, if you put the helicity of the flow to be 0, then this term vanishes. Then the growths are dictated by this function, the Bessel function of order 0. So Bessel function of order 0 is always less than 1. Okay, so therefore the eigenvalues will always get less than 1. So there is no interest in dynamo in this case. Let's say if we consider the fluctuation in the helicity, which are symmetric. Okay, then this you can do the averaging of this second term or the helicity fluctuation, which are odd in H. Okay, again that goes to 0, and again you don't find any interesting dynamo in this case. So only when we assume a scale separation, time scale separation between the helicity fluctuation and the velocity fluctuation, we see an interesting dynamo. Okay, so this is kind of a RG technique in this model we are applying. Okay, so what we do here is that the magnetic field is evolved from the, let's say, the interval 0 to 1 with a propagator G, where it is averaged over all the ensemble of the velocity field, okay, by keeping the helicity fixed. Because the helicity has the fluctuations now which are larger than the velocity field fluctuations. Okay, what we do here is, let's say if it is 2 times or m times, then we multiply m copies of G's, okay, and we obtain the general response tensor, and this response tensor we average over the helicity fluctuations, symmetric distribution of the helicity fluctuation. So if the helicity correlation time are m times the velocity correlation time, then m copies have to be multiplied and then the averaging has to be done. For the illustration purpose, we have considered the simple helicity distribution having a +1 and -1 with equal probability of occurrence of the helicity. And m indicates the time scale separation between the velocity fluctuation and the helicity fluctuation. So we looked at the limiting case first, when there is no shear and the correlation time is much smaller than 1. Basically this we did to compare it with the Kreitmann's case. You can see that in the Kreitmann's case, if you look at take the Fourier transform, you will get gamma, eta t, alpha square tau, k square term here. Okay. So we also get the similar kind of a term here. So you can see that the helicity fluctuation is contributing to the diffusivity. Okay. So only, let's say, and there is a m-1 that is appearing here. Only if m is greater than 1, only this term contributes. Okay. If there is no cyclic separation, then the helicity fluctuation will not make a contribution to the diffusion. So now we want to, okay, this is the important point, that the scale separations are very important to see an effect of reduced diffusivity. Okay. But our challenge was to show the dynamo without the negative diffusion. So we'll first derive the condition for this dynamo in this renovating flow model without the shear. At what values of m it can lead to the negative diffusion. So the growth rates when we plot, okay, the gamma is a growth rate, normalized growth rate with respect to the wave number. For the m equal to 5 and 6, there is no growth. For m equal to 7, there is a growth. That means for m equal to 6, meaning if the helicity fluctuations are 6 times more than the velocity fluctuations, then only a negative diffusion can occur. This is for the case of zero shear. Okay. So to show the dynamo, we have to keep the threshold value of m below this value 6. So this is for the case with shear. Okay, and we looked at the m equal to 2 case. We did not find the dynamo. The next thing that we found the dynamo is for m equal to 3. And the scale separation is 3 times. So what we plotted here is the axisymmetric growing mode for that kind of a spike distribution of helicity. So the color regions are the dynamo regions, okay, where the growths are occurring. So the K3 is in the z direction and the K1 is in the x direction. And the shear strength is varied from left to right, and you can see that the dynamo region increases and then it starts to decrease. The maximum of the wave number occurs on the K1 equal to 0 axis, okay, somewhere here. So hereafter we'll only look at the 1D dimension, 1D modes only, and this is equivalent to taking a planar average in this model. So to compare with the simulations. So if you look at the maximum growing wave vector, okay, this for example, as a function of shear, you can see that it has a non-monotonic behavior, okay. So the k star here is a scaled variable, that is k divided by the scale of the velocity field, okay. So here you can see that when if this k star is less than 1, that means the growth is happening at the larger scale, meaning it is happening for the scales which are larger than the turbulent scale. So this is a large scale dynamo, bona fide large scale dynamo. And you can see interestingly a non-monotonic behavior, that it increases with the shear and then it decreases. Interestingly, the growth rates of this maximum growing wave number as a function of shear also shows the non-monotonic behavior. For certain, till the certain value, for example, if you look at the m equal to 3 case, here there is no growth at all, okay, and only after certain threshold value of shear there is a growth. So I was talking about the growth rates, which has a non-monotonic behavior. If you look at the large value of the shear, okay, the growth rate increases and then it starts to decrease with certain power law. If you look at the velocity fields that I had introduced, so they have a quasi two-dimensional structure at the large value of the shear. And we know from the anti-dynamo theorem that the 2D turbulence cannot sustain the dynamo. Therefore, the dynamo at the large shear becomes inefficient. So simulations are generally in this region, okay. They always measure the growth rate which are linear in shear. But when we really go to the high values of shear, shear does not help the dynamo, it actually kills the dynamo, because it also kills the turbulence model. So if we contrast this case,
Naveen, excuse me, Naveen.
yeah,
Hello.
yeah, I can
Shahil
hear.
here. So,
Yeah,
yeah. Should I ask a question now or
yeah,
at the
sure,
end
sure,
of this?
sure, go ahead.
So can you tell us that what determines which factor actually determines that whether this growth rate should be linear one or the exponential one? Can you say that in general?
Now the growth in the, see, the plotting here gamma, it is exponential growth rate only.
Oh, okay,
So,
okay.
so that's why let's say here, when I, okay, here if you look at the dispersion relation, lambda, okay,
Mm,
which is 1 by
mm,
tau ln times the sigma. Sigmas are the eigenvalue. So the moment I
mm.
take the ln, it is, the sigmas are exponential times the lambda,
Okay,
which
okay,
is
okay.
exponential growth
Got it.
rates.
Right.
Okay, in 3D
And
turbulence, you will always have the exponential growth rate. Only in 2D turbulence, okay, even though there is no dynamo, you will have the transient effects. Okay, so there you
okay,
will have the algebraic growth rate, the linear growth rate, dynamo grows and then it actually decays.
right. And this decay, is it like this turbulence squeezing means and the flow, this Lorentz force is acting much on the fluid for means fluid
For
velocity
this, you
field?
are saying, no, see
Uh-huh.
this, all the calculations that we have done for the kinematic dynamo. So if you look at the velocity fields, okay, the Navier-Stokes equation that we have considered is the equation without the Lorentz force actually. See,
Oh,
we
okay,
want
okay.
to understand what is the mechanism that is responsible for the growth of the magnetic field. So we are not worrying about the
Okay.
saturation effects.
Right, right. Okay,
That is
thanks.
the next level problem. Okay,
Right,
even in this kinematic regime itself, because in the large shear, the flows are becoming kind of quasi two-dimensional. Okay,
right.
the it is dynamos are becoming inefficient. For really large values of shear, actually it kills the dynamo. You can see here, for example, the black curve. For the m equal to 3 case, the m equal to 3 is the helicity fluctuations are 3 times the velocity fluctuation. So for the really large value, there is no dynamo at all.
So you are saying this 3D problem becomes 2D one.
For the larger shear, yes.
Right. Okay. Okay. Thanks. Yeah. Please carry on.
So now if you contrast this with the case of the fixed helicity, okay, you can see that for the zero shear, there is a finite growth rate. Okay, but that was not the case for the fluctuating helicity case. For zero shear, the growth rate is 0. This sort of indicates that there is no negative diffusion in this turbulence. So here also it shows a non-monotonic behavior, but the fall with the larger shear is much shallower compared to the case of fluctuating helicity. Now if we compare this with the, let's say if I were to do the same calculation with the velocity fields without any shearing amplitudes, without any shearing of those amplitudes, I just consider the constant A, okay, which is isotropic. That's what they generally do in the modeling of the shear turbulence, that the shear they consider separately and the turbulence they consider isotropically. If they do it like that, then you can see that the growth rates are actually monotonic function of the shear. And because of this, it led to the conclusions that in astrophysical cases, the regions of the zones of high shear are the zones of the efficient dynamo. For example, in Sun, the tachocline are the zones of high shear. So people thought that that is where the most of the dynamo happens. But if you actually consider the effect of shear onto the turbulence, it actually kills the dynamo rather than helping it. Okay, this is the dynamo cycle period. Okay. Where I have plotted the cycle. Basically it indicates the pattern speed, the time period of the pattern speed. So at these smaller values of shear, you can see that it has a scaling of -1, and this is the scaling that is coming from the alpha omega dynamo. Okay, and the larger values of shear, it has kind of a flattening effect. Okay, this is happening both because of the memory effect that we have considered, and then because of the shear acting on the turbulence. So if you look at the tau very small case, 0.1, you can see this dot dot dash line. It actually monotonically decreasing. So only for the finite correlations time that there is a different trend that is seen in the cycle plot, and this has an implication for the magnetic activity cycles that are observed in this observation, which are recently published by Olspert in 2018. Okay. So now if you, okay, on the left, what I have shown is a simulation result from the Hughes and Proctor in 2009, where they plot the growth rate as a function of shear at the size of the box, picking, so that picks up the magnetic field, mean magnetic field. So for the smaller values of shear, they have no growth rate positive at all. That means there is no negative diffusion in their model. As the shear value increases, okay, the growth rate increases, and then for the really large value, they also see in the simulation actually, where they have considered all nonlinear effects and all. And they even have the rotation and the stratification in the simulation. Okay, they see a kind of a saturation effect in the growth rate with the large values of shear. So in this model also, I took the wave number to be 0.2, which is the largest scale, and plotted. So previous plots were for the maximum growing wave number. This is for the fixed K. You can see that for the smaller values of shear, the growth rates are negative. This indicates that there is no negative diffusion. It increases linearly and actually starts to decrease. And this particularly black curve, you can see that the growth rate actually decreases. So these are the conclusions that we show that in the non-helical turbulence, for the dynamo is actually insensitive to the fluid spectrum. Okay, and in the renovating flow model, we showed that for the negative diffusion, without the negative diffusion, we could trigger the dynamo mode. That was the challenge. This was the challenge that was considered in the thesis. And we saw that both the growth rates and the maximum growing wave numbers having a non-monotonic shear strength behavior with the shear strength. Okay. So I have already taken 1 hour of the time. Okay. So there is still another part where I have to talk about the spatial fluctuations of the helicity. I don't know, should I go on, or this is a good place also to stop? If there are questions, I can take it. Hello? Should I go on, or should I stop it here?
You want to go on, and you actually started 10 minutes late.
Okay, should I go on? Okay, fine.
Maybe like, can you finish in next 5 minutes?
Yeah, I'll try to.
Okay.
So now we look at the helicity fluctuations, temporal helicity fluctuations in the renovating flow model. Now we try to look at the spatial helicity fluctuations in the mean field setting. Okay. So we have the induction equation like this. Okay. We split the induction equation into mean and fluctuation using some Reynolds averaging rule. Then we get the equation for the mean field, which is same as the induction equation with the additional EMF term, which is quadratic in the fluctuation. Okay. And the B field, the small scale fields are obtained from the fluctuating part of the equation by dropping this nonlinear term under certain approximations. Let's not go into it now. So, yeah, so this EMF in the homogeneous and isotropic turbulence has this linear kind of a relation, where this alpha and eta t are the kinetic helicity and eta t are the turbulent diffusion, which I already introduced. Okay. And then what Kreitner did, as I already showed, that he did again the same kind of a technique for this mean field equation, where he split this mean field equation in itself into mean and the fluctuating part. Okay. So this will happen when we have certain dynamics or fluctuations which are larger than the turbulent fluctuation scales, and we obtained this negative diffusion equation. Okay. So the Moffat actually extended this to the spatial part of the alpha also. Okay, and there he obtained this kind of a induction equation itself. The structure of the equation is preserved, but this Vm and eta k depends on the alpha fluctuations basically. So the eta k is nothing but the Kreitner diffusivity, which is this term in the bracket, and the Vms are nothing but the gradients of these fluctuations. Okay, let's see when these gradients are non-zero. If there are, let's say, alpha fluctuations or helicity fluctuations which are varying over the length scale LA, whose amplitudes are varying. Okay, then in such a scenario, this quantity gets picked up. It shows up like a velocity field in the average magnetic field. So then the alpha correlated with the gradient of the alpha is non-zero. In such a case, if there are no gradients, then this Vm is zero. Okay. So this can happen in so in the local patch of the simulations, this cannot happen because the gradients are not possible there. But in real systems like galaxies or accretion disk, where there are naturally gradients in density, temperature, heat, and these gradients are needed in this system because of the deeper physical requirement that it has to be dynamically stable. There has to be heat and the angular momentum transport. So in such cases, these gradients can exist, and there could be gradients in this fluctuation also. So when such is the case, then you will have a a kind of a Moffat, a kind of a drift velocity that comes because of these gradients of the fluctuation. Okay, and the Moffat showed that in the delta correlated limit, these fluctuations only contribute to the phase of the dynamo wave. Okay. Then what we did was we extended this calculation to the finite correlation time effect with using the same splitting techniques that we did for the mean field. And then for the magnetic field, we obtain in the Fourier space the integral differential equation. The time part of the fluctuation is sitting here, and the space part of the fluctuation is sitting here. The time part of the the EMF is basically depends on whole history of the fluctuation. Okay, so the EMF depends on from whatever that is happening from the time 0 to time t. So there is a history that is important here. So we cannot really solve this, integral differential equation. So we make a perturbative expansion. To the zeroth order, we obtain the same Crichton-Moffat model. To the first order in tau alpha, only to first order in tau alpha, we extend this calculation. So then we find the dynamo with this Moffat drift that is coming because of these gradients in the fluctuation. Okay, in the strength when the alpha fluctuations are smaller compared to the diffusion strength. That is basically there is no negative diffusion. So this was one interesting proposal that came out, and it needs to be measured in the simulation also. So the interesting case, when we put the Moffat drift equal to 0 in this model, we find that there is no dynamo for the weak alpha fluctuations, meaning when there is no negative diffusion. So then this sort of hinted us to us then why all the predecessors, theoretical people who tried to attack this problem from the mean field setting failed to do so. That happened because they never consider this memory effect. Okay, so they never solve this full partial differential integral differential equation. They always made an expansion like this that we did, and they failed to find the dynamo in this case. Whereas when we start the analysis from the induction equation, okay, that itself is non-local in time when we derive the mean field from it. So Moffat drift was essential for the large-scale dynamo action. So here in this model, the pure temporal fluctuation of the helicity could not lead to the dynamo. Okay, we suspected that the locality assumption that we made in time is responsible that we did not find the dynamo for the pure temporal fluctuation. Okay. So this is the broad conclusion of the thesis. With the locality in time assumption, people had already found the helical dynamo, okay, by Steinbach, Cross, and Radler. People did the same, extended the same assumption to the non-helical case also, but they didn't find the dynamo. So what we did is we started with induction equation, which when we take the average of the induction equation, it naturally incorporates the memory effect of the turbulence in it. So therefore, we could find the dynamo. Okay. For the non-helical case, in helical case also we found the dynamo. Its non-local effects are shown in the signature of the cycle period at the large values of shear. Here also in the non-helical case, it shows the signature in the largest value of the shear. So these two regimes are the one which are explored in the thesis. Okay, I'll conclude here.
Okay, so are there any questions? Raise your hands, please. So it doesn't look like there are any questions.
Okay.
Oh, okay, Shahil wants to ask a question. Okay, go ahead, Shahil.
Thanks, sir. Yeah, so again, I'm asking a general question that you showed this growth of magnetic field and the saturation of magnetic fields. So, is it possible to apply, say, this
No, can you
saturation
repeat it?
magnetic field?
Voice is breaking. Hello.
Oh, okay. Can you hear me now clearly?
Now, yeah, yeah.
Yeah. So can you tell us that this saturation of magnetic field, does it depend on the value of the initial seed field or the strength of the initial velocity field?
The
Just
saturation
a
of the
general thought.
magnetic field, first of all, it doesn't depend on the initial seed field because there are simulations. For example, the Axel Brandenburg has done the simulation where they have seen that even if you take the seed field of the order of 10 to the power of minus 150, okay, they have seen that this field is
Hmm.
going up to the equipartition strength. So
Okay.
basically, it is
Okay.
decided by the how much energy is available in
So
the fluid.
like kinetic energy.
Yeah, how much kinetic energy is available in the fluid. Okay, that decides the and at what stage this back reaction can start happening. I think that
Okay.
depends on the
Okay.
RM value and RE value. RM value basically.
Right.
It
Right.
doesn't have to do
Okay.
with the seed field.
And
That much is clear.
acha. Okay. Right. And is it possible to have in a single simulation this both large scale and small scale dynamo effect?
Of course,
Is
of
it
course,
possible
of
to
course,
have?
of course. See, only in the this confusion came because of the mean field theory. Okay, in mean field theory, when you do this kind of a splitting, okay, you throw away that
Right.
non-linear term and you only consider there. You always take that the small scales are produced from the large scale, right?
Okay. Okay. Right.
So, for example, here, if you look at this, this fluctuating field equation, you throw this term, okay. This is called fossa approximation, and you only consider the fluctuations that are linear in B. So the small b is specify actually the average B itself. But in the actual simulation, okay, both are there. Both are there. For example, here itself I can show you the BRMS. Okay, the BRMS here, it is the total field. Okay, the mean plus the fluctuation. It is growing. So only when I take the average, I pick up the mean component, and you can see that the mean is growing much later compared to this BRMS. BRMS is already started growing here, and there is no growth in mean field here. Okay, mean field is coming much later. The fluctuations are already picking up. So there is always both. You will see small scale fluctuations and the large scale. Both you will see. Both will be seen. So if you start the analysis from the induction equation, let's say, and here induction equation, and if you define the 2-point correlator of the magnetic field, you can see that there is a scales like that happening. For example, Kandu has done this calculation in 2005. For example, if you remember the Kazantsay model, okay, this is a model for the small scale dynamo. He extended that model to the helical case also, okay, and there he shows that both small scale and the large scale can coexist together. Small scale are bound states, large scales happens because of the unbounded states in that solution. So they can exist together.
Right. And the last question, just a numerical one. So in your simulation, do you have this hyper dissipation terms, and do you check that how that hyper diffusion terms actually affect this saturation of the field or something, or growth scale?
See, our interest in this simulation was to look at the kinetic phase only, okay? And we are looking at the high RE case. It is already much larger. Sorry, small RE, low RE case, right? The diffusions are much stronger in our case here. So in our case, the Reynolds numbers are very moderate. We don't have to do such kind of an exercises. So only at high RE, really large values of the Reynolds number, you require such kind of hyper diffusions basically to cut off the energy piling up at the smaller scale.
Right. I got it. Didn't check this Reynolds number. Right. Okay. Thanks a lot.
Okay, Naveen, so there are no further questions. So let's just end this colloquium
Okay.
at this point.
Okay. Thank you.